Hi, hello, and welcome back to Science as Progress and Perspective. We've covered a lot of ground in the last two lectures, looking into a sort of new kind of realism for the 21st century, one that can replace this sort of what I call naive realism, what other people would maybe call strong realism of positivism. So I was introducing you to this idea of scientific perspectivism based on the books by Ron Geary and Bill Wimsatt, that we're assuming that there is sort of a unique causal structure to reality. We're assuming that we can have some sort of access to it, but we're acknowledging the fact that we're limited beings and we cannot step out of our own heads to get sort of a God's eye view or a view from nowhere on the world. I covered in the last lecture the idea of robustness of knowledge, that you can get knowledge that is sort of confirmed in many independent ways by observing something, deriving it, measuring it, all kinds of ways. And that it's very important that these different ways are independent. Often we mistake the independence of such confirmations. But the more such confirmations we have, the more trustworthy the knowledge is that we have. And there is no certainty, maybe not, it's impossible to get 100% certainty in empirical knowledge, but we can establish relative certainty. So we can establish the relative trustworthiness of knowledge. And some ways of knowing are more trustworthy than others. So there is no sort of postmodern relativism here. It is possible to decide very often, in most cases, what kind of approach is appropriate for a certain set of circumstances. We'll go into that a little more in future lectures. I said that most of science is not based on finding optimal solutions that solve a problem under all kinds of circumstances, but is sort of based on heuristics, solutions that are satisficing, that are just good enough for the problem at hand. They are much more sort of efficient to employ than these sort of unattainable optimal solutions that positivism, or sort of the standard view of science, would suggest we need. I was sort of explaining how a growing edifice of scientific knowledge can be built on top of robust sort of theories, hopefully. And that as those theories become the basis of other perspectives, other insights, they become what is called generatively entrenched. So if we remove them, a lot of other sort of pieces of insight that depend on them will also crumble. And I was also telling you how we can sort of learn from the biases and the errors of our sort of false models of reality that we have. We can learn from those errors and from comparing perspectives and models. We can learn, again, what is robust and where do we need work? Where are the parts of our knowledge that are not robust? Where are the gaps? And so by comparing perspectives, we can get things right, as Michele Massimi was putting it. So we can actually make progress, and we have to make errors to make progress, which is very important. This is going to come back when we talk in the last lecture about how academic research is actually set up at the moment, because it no longer allows us to make those errors that we need to actually make progress. And so, in the end of last lecture, I said perspectives and models are like maps. They are not necessarily true or false, but they are applicable and useful in certain circumstances. So we're going to use this to sort of turn our attention now from how maps, models represent reality to the activity of representing. A shift of focus from the products of science, facts that science is supposed to produce, to the process based on scientific practice. So we're going to look at science as an activity. And the sort of first question I would like to ask in this sort of context is, does scientific knowledge always increase? How does it actually evolve? How is it built? Does it always get better? Does it always get more? Does scientific knowledge progress towards a better understanding of reality? This is slightly different So we have more, but we also have more accurate knowledge. Is scientific progress rational? What do I mean by that? Is that, of course, the scientific method is rationally justified. But where do the questions come from that we have? Is that a completely rational process? This is a question that will keep us busy for quite some of the lectures that are to come now. Are scientific discoveries predictable? Is another interesting question. Can you say where science is going in the future? Does what we think is science change over time? That's another question. Does the scientific method itself change over time? So not just what we consider scientific, but the method of getting scientific insights, the criteria for accepting what it is about. And this is a question that may be worrying you as a researcher, will scientific discovery ever end? So if you're accepting this sort of view of positivism, we have, maybe it will not end, but we have certainly a law of diminishing returns, right? As we are approaching reality, we will get less and less, important corrections to our increasingly accurate theories of reality. So we established in the last lecture as well this doctrine of fallibilism, that no synthetic proposition is infallible. Empirical knowledge is always tentative and can never be absolutely certain. Again, we cannot be absolutely certain that fallibilism is true either, but we can be pretty certain. The evidence for this is pretty good from the history of science. And so we can think about how to judge progress in science. How should this work? It is pretty undeniable, if you're reasonable, that there is some empirical success. We are better at manipulating and predicting observable phenomena in our world than at any time in the past. It doesn't mean we're good, or manipulation and control is a good way to go about living in the world, but it definitely means that we have better healthcare, for example. We have better technology. So really applied sort of empirical successes. Science works in many ways. And that is just, unless you're really, crazy, really, you cannot deny this fact. Often, people who claim they don't believe in science, they still go to the doctor. They still believe in gravity. They don't step out of a third floor window. And so we can say, okay, historically, there is progress. Science works in this sort of very pragmatic way. But does that mean, that's not an obvious question, whether that means, does that mean we also have a better understanding of how the world really is? It could be that we just get lucky. We have completely wrong theories, but they work to solve our pragmatic, practical problems, okay? And does it mean that our scientific theories get at least something right in the sense of Massimi? Is there stuff we actually know about reality in this way? Solidly, knowledge we can really trust. We don't have to revise in the future. Those are difficult questions. We visited them, for example, when we went through the problem of induction and the new riddle of induction already. So let's take a little bit of a different angle here. So let's ask, what is it that these theories get right? What does it mean to get something increasingly right? So I could give you this sort of definition, which I took from the textbook, The Introduction to History and Philosophy of Science, which says an empirical theory is scientific if it explains by and large the known facts of its domain, and it is testable, in a Popperian sense, falsifiable, at least in principle. Okay, so it must have some explanatory power. It must do something for us, and it must be falsifiable. Otherwise, it is not a scientific theory. Okay, so this is a good working definition. Now we have to sort of go a little bit deeper into a topic that I actually mentioned before already, and that is the sort of opposition between what we call scientific realism versus instrumentalism, which is something that's also sometimes called anti-realism. I really don't like this word because it's misleading. Let me explain. The difference between those two views is all about the unobservable parts of our theories. So unobservables are those sort of entities, structures, processes that are postulated in scientific theory, but whose existence cannot be directly detected by our senses. So we have to sort of infer them indirectly. So that would mean, in Wimsatt's term, that they're automatically a little less robust than observable phenomena, because there are less independent ways probably to establish them initially, but maybe they grow to become really robust. So there are unobservables like energy or mass in physics that are extremely well established in science. Fitness is a more controversial sort of unobservable in biology. There's a lot of dispute about what makes an organism fit in an evolutionary sense, or a population. And some of these unobservables cannot even be observed in principle. For example, space-time itself. We have to accept it as a given. It is required for us to even be able to think about the universe, the world we live in. So do our scientific theories correctly describe both observables and unobservables? That's the difference between realism and instrumentalism. So scientific realists would say yes, okay, if we robustly describe something, so it shows up in our theories over and over again, it becomes really fundamental, like energy and mass in physics. Those sort of terms must apply to something in reality. And instrumentalists say, no, we can't. These are just, these concepts, mass, energy, maybe an electron. That's just, a concept we use, and it allows us to get the observed phenomena right, but it doesn't necessarily have its own independent existence. So once again, this is very important. Anti-realism, instrumentalism, people who adhere to those sort of doctrines, they don't think that there is no reality out there. They just think that our theories, the unobservable parts of our theories, don't really refer to anything that's out there. That's sort of quotation marks. And I should also say that, you can be a realist or an instrumentalist about different concepts. So I give you a personal example. I would pretty much, believe, as a biologist, I'm not, qualified, but I would believe that forces like the force of gravity are real. On the other hand, there's this concept called information. And I don't believe we should reify information. I don't think information is a thing that is real or out there. It's a way, looking at the world as a flow of information is a way of explaining certain phenomena. But information is not a thing for me personally. We could go on about this forever, but all I want to say here is that you can have different preferences, and you can mix and match your realism and your instrumentalism. When I talked about perspectival realism before, what's important is that at least some of the theories that we have refer to something, in reality. And we'll come back to that point. It basically means that we're not only judging the validity of our scientific theories based on their practical value. That's an important distinction to make. So let's have a look at something really fundamental, like the standard model of elementary particles in physics. So a lot of theoretical physicists believe that, everything in the world, we should have a theory that explains those particles, a minimal set of such particles, and you should be able to derive everything else, the whole of physics, from such a fundamental set of entities, a minimal set of such entities. And so currently, the way this model stands is you have a whole zoo of different fundamental particles, which remain themselves sort of unexplained, but combinations of those particles give you the phenomena of the world, right? You have quarks, leptons, gauge bosons, they're also called vector bosons, and scalar bosons, like the Higgs that was recently confirmed in a high energy experiment. So we have experimental evidence. They're not just theoretical entities, those particles. You can do experiments to sort of show that they exist, but nobody's ever seen them. They're not observable, okay? So they're inferred. They're constructs in the fundamental theories of physics that allow us to derive a really powerful set of phenomena. Okay, so we're striving, they provide a big unification of phenomena, basically. We're striving to explain a lot of different phenomena in one fundamental framework. And that's a pretty powerful sort of model of reality here. A very broad model that we call, of course, a theory. But do they really exist out there? Or are these just constructs that we use to explain the phenomena? The sort of most famous argument to say that they must exist is the so-called no miracles argument, okay? So basically, this says science gets so many things right. The empirical success of science throughout history is so impressive that it would be basically a miracle if the things, the unobservables that scientific theories don't, that they relate to, that they use, don't correspond to anything in reality. So here's Hilary Putnam again, writing, the positive argument for realism is that it is the only philosophy that doesn't make the success of science a miracle. Quite simply. That's quite pragmatic. Okay, so it's likely. It's just more reasonable. It's more probable to assume that those entities refer to something real. It's not really satisfactory, and you can have a very sort of opposing view to this. Here is Larry Lawton, and he is famous for what is called the pessimistic meta-induction. And so Lawton writes, from the point of view of the present, most past theories must be considered false. Newton's mechanics, one of the most firmest established theories in the history of science, was overturned. Indeed, this will be true from the point of view of most times. Okay, there's a problem. So whatever we believe today to be true, why should that be privileged? Why should that be different from theories at other times in history where we have empirical evidence from the history of science that show that most of those theories have been overturned in many ways? Therefore, by inductive generalization, surely theories at any given level, any given time will ultimately be replaced and regarded as false from some future perspective. Okay, you see that this is not a principle. I mean, it is falling prey to the problem of induction, of course. We cannot guarantee from looking at the past what the future will bring. But it's not an unreasonable view, okay? If we look empirically at the history of science, a lot of the theories that we had were overturned, and so there's no reason to think we live in privileged times. That's why it's called pessimistic, okay? Everything we know will always be wrong. But that's an extreme view, okay? Current theories are also false. That's just a very, very sort of generic and extreme view, because what actually happened when Newtonian physics got replaced by general relativity, depicted by these sort of rubber sheet of space-time here. It's not like we threw out everything, I mean, you can approximate, at lower than light speed velocities. You can approximate most of relativity with Newtonian mechanics. You can, shoot space probes to Pluto using Newtonian mechanics. So past theories were mostly not absolutely false. They were false in certain aspects. For example, Newtonian physics involved this sort of mysterious action at a distance through forces that wasn't explained, and that the theory of relativity explains better. So they were not just abandoned. I know of not a single case of a scientific theory that was just thrown away without a replacement, without an alternative that the community actually deemed to be better than the old theory. And we talked about some of these zombie theories like rational choice theory and linear genotype-phenotype models in a previous lecture. They stick around, although everybody knows they should be falsified. They have been falsified many times. They're wrong. They're not just, abstracted from reality. They're idealized to a point where they really don't represent anything, and we know that. Okay, so there is probably some sort of scientific progress after all. Okay, because we replace old theories only by theories that we think are better than those old theories. They solve a number of problems that the old theories have. So let's try and make this idea of progress a little bit more concrete. So before we do that, just to come back to this point, this solves the second problem of relativism. The first problem was that scientific knowledge, if you're a relativist, then you're thinking this is just another culturally determined way of knowing. It's completely socially constructed, it's completely arbitrary. And the second problem is that you don't believe in progress. You don't believe that our views of the world are becoming better over time, because it's just all is just dependent on the current context. And to judge whether a society is better now or 1,000 years ago is absurd. I don't think that's a view that people actually hold. They pretend to hold it because it's completely absurd. Of course, knowledge progresses. And here we have a way of looking at that. If we focus, again, from the output, the facts that science produces, to the process of how those facts are produced. So what's really important here is that we make this switch. We look not just at science, but at science and at scientific knowledge, as a process, not a fixed set of facts. Okay, so we need to come up with a concept of what I will call processual knowledge. And here is Nicholas Rescher, process philosopher, and he writes, the history of science and human inquiry in all its forms clearly shows that facts, theories, concepts, and methods are not entities with a fixed and stable nature, but process-geared eventuations that changeably reflect the cognitive state of the art of a place, time, and cultural modus operandi. What appear as the timeless truths of one era are merely transitory beliefs from the vantage point of another. So this sounds a little bit like Laudan's pessimistic meta-induction, but it's less radical. It doesn't say everything is always wrong. It just says whatever knowledge you have right now is just a snapshot of a larger process. And you need to understand this sort of larger process of how knowledge evolves in science if you want to understand scientific knowledge itself. The actual nature of the world's furnishings outruns our current knowledge of them. So nature is always a step ahead because we're limited beings with limited experience. Our knowledge of fact is always in flux. It is not a thing, a definitive corpus, but an ever-changing and ever-growing manifold of process. Beautifully put, but very counterintuitive. So scientific knowledge, as I told you before, is never absolute, but it's always in flux, always tentative, always changing. The processual nature of knowledge reflects the fact that our thought about the real things of this world presses outward beyond the limit of any restrictive boundaries. Okay, so this process, that's why I call it open inquiry, will never, ever stop. And this Rescher calls cognitive inexhaustibility. Basically, there is much more than we can ever know. In fact, in another book called Unknowability, he argues that there is an infinite number of things that we could potentially know about the universe, but our language restricts us as finite beings to a finite number of truths that we can establish. And so there will always be an infinite number of facts about the universe that we will never know. And so science progresses like ripples in a pond. This is a metaphor taken from Stuart Firestein's beautiful and very accessible book called Ignorance and How It Drives Science. Come back to that. This picture that scientific knowledge expands outward like ripples in a pond. And as they expand, of course, the circumference becomes larger. So what the area that's enclosed in them becomes larger, but also the border to the unknown. So the more we know, the more we are aware of what we don't know, and the more contact we have with the unknown. So science and scientific knowledge are both processes that will go on and on and on. But they don't really grow like ripples in a pond, really sort of smoothly. But they move in sort of jerks and spasms. And those, famously, are scientific revolutions. And here we come to the philosopher of science that's the second most famous philosopher of science after Karl Popper. Some of you may have named him as someone you know as a philosopher of science, Thomas Kuhn. Writing in the 1960s, he says science is not only development by accumulation. It's not this sort of expanding ripple in the pond is not a smooth sort of process, although that happens. And he calls these phases of science normal science, which involves puzzle solving within a present paradigm, a present set of theories, a present worldview, a present episteme. And within that, you work out problems. Okay, so this is the sort of science you can do pretty automatically. Periods of conceptual continuity like that, though, are interrupted by crises, triggering periods of revolutionary science. And those Kuhn, in his Structure of Scientific Revolutions, famously calls paradigm shifts. He's not quite clear in the book about what a paradigm exactly is, and he's been criticized for this. But one thing is clear. The world that we view before and after the revolution is what he calls incommensurable. Okay, remember that we actually brought Kuhn up before when I talked about the theory ladenness of knowledge. And he said, if you have different background theories, you will see and want to measure different things. For example, in the pendulum that we were discussing, the Aristotelian and the Newtonian scientists measuring a pendulum, remember that. And because different aspects of the system are salient to these different scientists, they live in different worlds, basically. They see a different world and their views are incommensurable. They're not comparable. They can't sit at the same table and discuss because their concepts refer to different things. That's quite radical. And we're not quite sure if it's always the case. I mean, there's always some sort of translatability before and after the revolution. But what is sure here is that new paradigms allow us to ask completely new questions that go beyond puzzle solving. They change the very questions that science asks. And so that's very important. They allow to see us old problems in completely new ways. The world has really changed because we have changed through the process of the revolution. Our, cognitive abilities have changed. But they also mean that some questions from the old paradigm become meaningless. So the resting place of a body in Aristotelian physics is completely a meaningless point in Newtonian physics. It will just follow unaccelerated on a constant speed and trajectory if it's not influenced by any forces. So completely incommensurable views of the world. So this sort of contrast between normal science and revolutionary science, this is central, okay? And this is a process that's deeply embedded in the social circumstances of science. So it's not just pure Popperian falsificationism, but a lot of things have to accumulate and go wrong for a revolution to occur. And again, revolutions only occur if there's a better alternative to replace an old worldview. We are not just going to abandon the worldview that we have. And we can look at that again in the history of science. The most famous sort of paradigm shift is probably the shift from the Aristotelian-Medieval view of the world to a modern mechanistic view of the world, Newtonian Cartesian sort of view of the world. But not only did our view of the world change, in Aristotelian physics, you have sort of terrestrial domain with the four elements, water, air, earth, and fire, and then the celestial domain with the ether, the eternal fifth element. And those are completely different. So the world is not uniform. You have these perfect spheres on top the sphere of the heavens and the planets and the sun and the moon below. And you have a certain method also associated with this worldview. Again, this is from the Introduction to History and Philosophy of Science, which beautifully describes this transition. The method at that time was that a new theory was accepted if it grasped the nature of a thing through intuition schooled by experience. So the source of all knowledge was experience, and you needed to train that experience. You needed that experience, to train intuition. Okay, that is a completely different way of accepting theories after scientific revolution has occurred. We are in the Newtonian worldview. And not only is it a mechanistic worldview, a uniform world, the Earth has been taken out of the center of the world, but also does it have a completely different sort of method, scientific method or meta method, that says a new theory is only accepted if its predictions are confirmed by observations and experiments. If you think at the collision between Galileo and the church, there were two really different worldviews colliding. Not just did these people see the world with different eyes, they had a different model of the world, but they also had different methods of establishing scientific truths. We'll come back to the question whether there are sort of values or behind this method that are universal, that go through the history of science. But at this point, I can only stress how much what we consider to be science and scientific knowledge has changed over time. Not always in a rational sort of way, but often through complete sort of revolutions in our worldview that completely overturn the world we live in. To put it in Yogi Berra's world, the future ain't what it used to be after the revolution. In fact, the world ain't what it used to be. Because of this theory-ladenness of our knowledge, we will perceive the world in a different way, see it literally through different eyes after the revolution has occurred. This is pretty fascinating, but it comes with all kinds of problems for the demarcation problem. How can we demarcate what is valid science if it constantly changes over time? Not just the boundary of scientific knowledge, the facts we know, but the very methods that we use to come to these facts have radically changed. Our idea of what is natural has changed. So to just come back to this point of is this process then rational and predictable? We get back to Rescher, who says in his book, if you could predict scientific discoveries, you'd already have made them. Okay, so there's a logical paradox in this idea that science proceeds rationally. If it would, you could predict what it will discover. And so you would already have made the discoveries if you would only know enough. But this is in principle impossible. And Rescher writes, the future of science is an enigma. Innovation is the very name of the game. Not only do these theses and themes of science change, but so do the very questions that we can ask through those revolutions. So it's completely impossible to predict, and progress in science is neither gradual nor rationally predictable. So this has pretty radical, repercussions for this idea that we can define scientific knowledge in a sort of an abstract way. This is a set of true propositions, something like that. And if we take this serious, it means that we need to look at the history of science, the process of science, if we want to learn what the best way of doing science is. And it will not be the perfect way of doing science because it will be biased by our history and our communities that have been doing science. But it will be the best view of science we can get, the best view of knowledge we can get. But we can only get it if we look at the process, the activity of doing science. And so this is where we will leave it here. Okay. It seems trivial when I tell you this, but it's a pretty radical sort of switch that you need to make from thinking of science and its, the knowledge that it produces as a thing, as a set of insights, as a sort of, set of true facts, something abstract, to this sort of living, evolving process, the activity of actual historical scientists. So what we will do is we will first have a little excursion into the philosophy of process. I will establish a few principles and show you why it is difficult to think about processes in the first place, and what are the obstacles that we need to overcome. And then I wanted to do two things. I want to give you a brief example of what this sort of switch in your view from things, from facts, to the process, the activity of doing science, what it actually does for a science. We're going to look at biology because I'm a biologist, but I'm going to give you a very broad example that everybody can understand. And what we're going to do then is we're going to turn our eyes back to this process that Rescher describes, this process of doing science, science as a process itself. And that will be the topic of the last lectures of this course. So I hope you will tune in again when we'll talk about process next time. But for now, thank you for listening and goodbye.